Right? I'll just call you on your phone as well, by the way.
Yeah, I'm streaming. Okay. Hello? Yeah, yeah. Yeah, fine, fine. All right. Okay, I'll share the link now. Yep. Wait, I don't wanna. Wait one sec. Oh, wait, I sent it in the wrong group, I guess. One sec. Oh, yeah, yeah, just do that, no? I think so. Yeah, I can. Yeah, it's exactly zero. Yeah. Yeah, I wish it was like this for the rest of the stream. That would be nice. Yeah. I was about to ask that as well. I think like when we switch, we'll just ask if anybody has questions every time we switch. Oh, somebody said hi. Hi. It's not there? Okay. Oh, okay. Yeah. That's over. I see. I see. I see. Okay. But are you able to see the stream? Okay. No, there's like four people in the chat. Yeah. Oh, yeah. Five concurrent viewers. Yeah. I see. Yeah. I'll type in. Oh, okay. What is 15 people? Oh, okay. Oh, that's not bad. Okay. And approximately a huge number of people have not seen the message. Yeah. Wait, let me see. My message itself, like, okay, a lot of people did see what. They just put, unmute and say we'll start in 5 minutes or something. Yeah, I typed it in the chat. We'll start in 5 minutes. Oh, you did? Yeah. Because I can't. I like see nothing on my phone. Okay. Hey, let me ask, how many people are actually there that are not from Horizon? Everyone. No. Sorry. Um, But you can see who is watching. Yeah, some people are typing. Okay. Um, I have no clue how any of this works. I should, return to the 18th century. It would be nice. Maybe I could discover quantum mechanics as well if I went back to the 18th century. Yeah. And we could take the lecture like that one. Yeah. That would be good. Indeed. It'd be beautiful. We have 8 viewers, bro. Okay. Okay, it's reaching double digits eventually. Yeah. You want to tag at all? At all, okay. Should we? It's kind of cursed, but yeah, I don't know, your choice. Let us see what. Okay, if everyone has tagged at all, unfortunately. Oh, then okay, then do. I hate this. I really hate this. My brain hurts. This is like an affront to my basic principles. There was a group called Group. Do you know that? Clue. There was a group called Group in the C5 summit. Yeah. Yep. Who came up with such a beautiful name? I do not know. Mm-hmm. When will the class end? It's 11 now. Huh? Yeah, it should be. It's 11. Uh, do we start? I don't know. Ask Ananya. Wait, I'll add him here. Simplest option. He had been summoned. If the question is if he's going to respond. Else we'll start it at 6:15. Like through everything. Okay. We feel that there's an amazing option called rewind, which even I know about. Why do they have to rewind? What? No, if they join late, just tell them rewind buttons. Do that. Okay. Yeah. Hello, Anika. Yeah. Yeah. So when should we start? Like there are right now like 11 people. Okay. Wait, you first six. Your voice is breaking. It's fine. Yeah, my net is not very good. Just a second. Yeah. Not it out. Let's start. We can start. What? Should we just start now? Yeah. Okay. All right. And we leave this call then, Ranesh. Yeah. All right. Okay. Wait. Pretty sure I was unmuted. Okay, wait. Can you hear me, everybody? If you can hear me, just say something in the chat, and then we'll start. Done, huh? Is that? Wait,
You can be heard.
I'm heard in the stream.
Yeah.
All right. So I'll get into it. Be a bit louder, okay? I'll be louder. I'll be louder. There's a few 12th and 11th grade people. Okay. That's very cool. That's very cool. Yeah, fine. Uh, so how do we do the doubts thing? Okay. So if you have any doubts, you can just drop a message. I'll after I won't be able to like get back to it immediately. I'll go through my slides, and then maybe after every 5 minutes I'll look into the chat and I'll see the doubts. And I'm guessing there's by seeing the demographics, there are 11th and 12th grade people. So you can ask your doubts. We won't judge. I mean, it's I don't expect you to, guys to like know too much about this stuff. So like feel free to ask any doubts. And it's not like we have any time constraint and stuff. Yeah. So yeah, Ranesh is also audible. Yeah. All right, I'll get into it. Okay. Yeah, so this is the final lecture of summer school, and you should have seen the title by now, but it's if you haven't, it's quantum computing and a bit of basics of quantum mechanics and stuff like that. And so it's a pretty interesting topic, I feel. Recently there have been a lot of developments in this field and stuff like that. And yeah, through Horizon. Uh, we'll be presenting now our basics, our the knowledge we have about quantum mechanics to spread word, and yeah, hope you guys enjoy and learn something out of it. I'll be starting first. I'll be presenting and initially talking about the language of quantum states, or basically when we start talking about quantum computing and start working with quantum computing, we need some notations and ways to describe what we're doing in quantum computing. So for that the language is necessary. Similarly, similar to like math and stuff, when we develop a new field of math, we need some sort of notation to express what we're talking about. So even for quantum computing, we have our own um, language to talk about quantum computing, and it's similar to I mean, it's used in quantum mechanics and stuff. So yeah, I'll be starting with that. So the first uh, this slide is just about the very basic notations and formats of quantum computing and quantum mechanics. uh, so this thing is known as the Ket notation, Ket and stuff. Very important Ket notation. You're going to see this everywhere if you get into quantum computing. And Ket notation is this visually, and this describes the state of something in mechanics, like basically anything. But it's used to describe the state, which we'll get into. But uh, just for now, just look at how, just try to understand how it looks like, and uh, get the feel of it. Similar, like it looks pretty similar to the vector representations of stuff, if you remember from coordinate geometry, where we have some representing something in the 2D Cartesian plane. We say something like ax plus by. Like similar to that, we have something that looks along the same lines. We have some alpha 0 plus beta 1, and similar to, again, to the vector notation, this can also be represented in the matrix form. I'm pretty sure the 12th graders would know about this. Not sure if the 11th people would know about this, but we often use matrices and stuff to represent vectors to uh, make some calculations easier or something like that. So similarly over here we have this Ket notation, this weird bracket, and it looks analogous to vectors, and it can be represented in the matrix form as well. And there's this other thing which is the bra, and it's kind of like the opposite of this. And basically this signifies the conjugate of alpha and beta in this form, in this matrix. I mean, it's uh, yeah, that's basically it. There's not it's This bra is relatively not too important compared to Ket, or this lecture at least. But for now, just uh, go with Ket notation. And there's this thing known as the inner product, where you multiply these two matrices, and and you take the mod of it basically, and that should just turn out to be uh, alpha alpha star, alpha alpha conjugate plus beta beta conjugate mod, if you do the matrix multiplication. Nothing too serious. This is not too important. Um, Now there's some new words called Hilbert space and stuff like that. So we we're trying to, so like when you guys have done like complex numbers and Cartesian or just non-complex numbers like real numbers and stuff like that, you would have noticed when we like deal with complex numbers, the plane is a bit different. It's a complex plane. And when we use real numbers, when we're doing coordinate geometry, it looks a bit different. There's no complex numbers and the thing. So it's always good to define the space in which we're working. And so we say that these states, they live in a complex vector space called Hilbert space. It's nothing to stress about. It's just words, but uh, eventually you will see that these alpha and beta are complex numbers. I mean, because there's conjugative, and so we use this space, which is the complex vector space, to do all our calculations and stuff like that. And for a single qubit, the space is two-dimensional. Again, nothing too much to worry about here. And this condition, for any state in quantum mechanics and stuff like that, we have this normalization condition, which is the inner product over here. Okay, we'll get into why this exists, but for now, the normalization condition requires that the inner product of any state with itself is going to be equal to 1. Or if you take this complex vector space, in that this state vector will be equal to the length of the state vector will be equal to 1. Or basically mod alpha square plus mod beta square equal to 1. If you do this matrix multiplication and just do this inner product, you'll get that basically. That we'll get into why that exists right now. So uh, I was talking about um, a single state right now, a single state system. Now I'll be getting into wait, sorry. I'll be continuing with the single state for. I'm just going to give some other notations and stuff. So similar to the previous example where I told you like that it looks something like a vector which we used in coordinate geometry and stuff. Uh, this also has something known as the computational basis. Like in when we were dealing with coordinate geometry, like I mentioned, we take a random vector, say ax plus by. Our x and y would be the kind of like the basis or like the axis and stuff like that. So similar to that analogy, in this case, we have our zero and our ones being the basis. And this is getting into like I mean computing, how our in classical computing we have 0 and 1 as the foundations. Here too, the 0 and the 1 will represent something, and we'll be doing computing work with that. But for now, we'll just say that mathematically they are defined as our computational basis, and they're orthogonal states. And there's this thing known as the superposition principle, which is very important to this is probably the most important thing in quantum as the foundation of quantum computing. And I won't be surprised if some people have heard about this principle, because if you've heard of quantum computing, you must have definitely heard about being able to be in the both 0 and 1 at the same time, or something like that. And that's pretty true. So our foundation, or our like classically we use our computational foundation as a bit, which is the very like that's the bits are the building blocks of computing, and the quantum version of that would be a qubit. And these qubits uh, are and can be in both the 0 and 1 at the same time, and that's due to the superposition principle. And yeah, so if uh, this is pretty common and many people know about this now. So when we say that it's in the what we mean by superposition principle is that it's the final state vector is in a linear combination of both the 0 state and the 1 state. And if you don't know what linear combination means, it's just that we don't have any higher powers of 0 and 1 and stuff like that. It's just some constant into 0 plus some constant into 1. And that's the very very basics of quantum computing. And so we'll formally give some names to what alpha and beta are. Alpha and beta in physics and quantum mechanics, they are known as the probability amplitudes. They're not just some random numbers, and they are complex numbers. And yeah, so I'll be getting into what they physically are, but let's just call them probability amplitudes for now. It's a hint. And The normalization constraint, if you remember, this inner product is equal to 1, and modulus of the inner product is equal to 1. That basically gives us alpha conjugate plus beta conjugate is equal to 1. And if you remember the for I think 11th grade, 12th grade, I don't know. If you guys are doing JU, you must know the identity. Alpha conjugate plus alpha conjugate is just mod alpha square, and similarly beta conjugate is just mod beta square. So we end up with mod alpha square plus mod beta square is equal to 1. And something else that always must add up to 1 is the probability of events, which now it's correlation is happening. So uh, yeah, so when we you know put the math with the physics, we end up and we realize that mod alpha square and mod beta square actually represents the probabilities of measuring 0 and 1, uh, which I'll be getting into right now. So so we know, okay, now if you guys didn't know, I mean, at least now we know that okay, a qubit can be in both the 0 and 1 state at the same time. And yeah, that's pretty interesting. It's different from what we do normally. But there is something that uh, not many people have heard about, but that is also a very important part of quantum. The way we use qubits, and it goes like this. So when we measure a qubit, we end up with either a 0 or 1, and the qubit is not in a linear combination of either state anymore. It just drops to one of the values, 0 or 1, when we measure the qubit. So when we are not looking at the qubit, it can be in both the uh, it can be in both the states, 0 or 1. But when we end up measuring the qubit, it collapses to either 0 or 1. And yeah, so that's kind of like a drawback to the qubit. It's not too much of a drawback, but it's a fundamental feature of it. And yeah, that's all just basic QM principles and stuff like that. And so the way this qubit drops to 0 or 1 when we measure it is not random. It actually depends on the coefficients alpha and beta, and that's where they um, get their name, probability, amplitudes, and stuff like that. So uh, we we figure out that mod alpha square and mod beta square actually represents the probabilities with which the measurement collapses the state vector to 0 or 1. So basically, if mod alpha square tells us the probability of when we and eventually measure this qubit, what is the probability of it collapsing to 0, or and beta square respectively for 1. So if mod alpha square is 1, then every time you read this qubit, it's going to be 0 for sure. And if mod beta square is 1, every time we read this qubit, it's going to be 1 for sure. So that's pretty interesting, and that's not very intuitive. Measuring the qubit, when we measure it, it collapses to either a 0 or 1. That seems kind of absurd, and yeah, that's basically how the entire quantum mechanics and stuff works. It's not very intuitive and doesn't feel right. Yeah, that's just how the world is. So I just finished a single qubit system, and now I'll be getting into what we can do with two qubits. And there is this is just notation again for representing two qubits, and this notation is actually important. It's not just uh, some random stuff. It's because there is this very important phenomena in which qubits can do uh, when they are next to each other or when they interact and stuff. So we have to kind of try to characterize uh, two qubits and one qubit separately and stuff like that. And it's important to develop two qubit and further qubit notation, because there's very different ways these two qubits can interact. So like, I mean, I think another example would be like, if you have two vectors, and you can either have a dot product between them, you can have a cross product between them, and the interactions, the way you say multiplication between them is different. You have to develop notation to say, okay, this is a dot product, this is a cross product, because the two types of interactions are different. So similar to that, uh, when we uh, uh, when we have two independent qubits that are like not interacted with each other, we use this symbol known as a tensor product, which looks like this. And this is how we signify it. So we have a qubit like this, qubit like this in the zero state, and we just use this symbol over here. Can also use this symbol, can also use this symbol, and yeah, which we can also use, we can use this symbol as well. This is all equivalent, and this represents two independent qubits. Uh, Now there's this other phenomenon which I was talking about, and similar like to the dot and cross product. This phenomena or this interaction between two qubits is very important, and we'll be getting into it later. And you must have heard it by now. There's no chance you haven't heard it by now. It's known as entanglement, and it's again a very cool property or feature of quantum mechanics where these two qubits somehow they get entangled with each other when they interact, and they're not two independent qubits anymore. So the measurement of one qubit affects the other qubit and stuff like that. So we can't use the old notation of two independent qubits with the tensor product anymore. So to represent that, again, we don't have to develop anything too much, but you'll see that these sort of states, okay, this is an example of an entangled state. This cannot be factored into two different uh, 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 states, if that makes sense. Like if you see this, it doesn't, it's not the multiplication of two different states, like similar to like, I guess x square plus y square, we can't factorize that. X square minus y square is just x plus y, x minus y, but x square plus y square can't in factor it into two independent states. Similar, so this is an example of an entangled state where it's not they're not two independent states. They're just it's just one state, and the two qubits are entangled. And I forgot to mention, I guess, but this is the general two qubit state. So for the single qubit state, we have alpha 0 plus beta 1. But now and that qubit could only take values between 0 and 1. Like either it could be, when we measure it, it would either be 0 or 1. But now these two qubits, the total number of variations these two qubits would have would be 0 0 0 1 1 0 1 1. And there has to be a probability at of which when we measure we end up with one of those states. So there are these four states which with their corresponding probability amplitudes, which tell us what is the probability of actually, I mean, the square of the mod, whatever. These numbers, their coefficients, kind of give us an idea of what uh, what would be the probability of ending up with this state when we measure the qubit finally. Yeah, so that's basically that's it. Another important thing which we'll be using a bit later in the lecture is phase, and there are two types of phases, and there's one really important one, one very useless one, and I'll just go back a bit. Mm, so over here we have this general state of uh, the state vector, psi is equal to alpha 0 plus beta 1. And I mentioned that alpha and beta are probability amplitudes. Now, when we talk about phase, I'll be talking about relative phase right now. Relative phase kind of gives us an idea about the relationship between beta and alpha, if that makes any sense. So, if you've heard about phase in your studies till now, it must have been, or at least you must have heard it in wave mechanics and stuff like that. And in wave mechanics, I mean, why does stuff from wave mechanics end up over here? It's because uh, there's wave nature in quantum mechanics and small stuff like qubits. So essentially, when we talk about relative phase, we're talking about a relationship between beta and alpha, and it boils down to it comes down, it's all caused because of the wave nature of quantum mechanics. Mathematically, because beta and alpha are complex numbers, if you remember the Euler's notation, we have beta is equal to, we'll write alpha is equal to some mod alpha e to the power I theta 1, and beta is equal to mod beta I to the power I theta 2. So the phase is just going to be theta 2 minus theta 1. It's the relationship between the uh, angles of the Euler representation of alpha and beta. That's the relative phase. If you don't want to get into all of that stuff, let's just say alpha is like uh, 1, beta is -1. There's like a phase difference of pi because e to the power I pi is equal to -1. Uh, Similarly, if alpha is equal to 1, beta is equal to, I mean, wait, you have to do the normalization condition, my bad. 1 by root 2 to all of that. And if we have alpha is 1, beta is 0, then we have a phase difference of uh, I guess pi by 2. Yeah. And yeah, uh, that's basically it. So that's the uh, angle between the two vectors in the Euler notation and stuff like that. That's important. Another thing is global phase, which is just basically if I take this state and I multiply it with some number, like any number, any complex number, any real number, uh, that multiplied number is known as the global phase, and it really doesn't matter. Like I could just take this psi and then multiply it with phi, or like some like 15, 200 and stuff. That it's pretty useless. It doesn't signify anything. Normalization and stuff matters. So it's like it really doesn't matter. I put a minus, really doesn't matter. But if there's a difference between beta and alpha, it matters because of interference and stuff like that, wave mechanics. It's essential, and you'll see that later on. So that's phase. Yeah, like pi by 2 phase, pi by 2 phase. This is pi phase. This is pi phase. Just look at this would be e to the power I 0, you know. So there'd be a pi phase over here, difference here, pi by 2, pi by 2, pi by 2. And yeah. So finally, I'll just be summarizing what we learned about qubits, and I'll give some real-world qubit implementations. So a qubit is the fundamental unit of information in quantum computing. Uh, yep. So we have classically we have bits. In quantum computing, we have qubits. They're going to be the building blocks of all our quantum computers and all our calculations later on. Classically, bits store either 0 or 1. Qubits can represent both 0 1. Using the superposition principle, it can be in both states at the same time. And uh, yeah, so that all exists because of the superposition and superposition principle, which is new. Must have heard it. And finally, the thing that uh, kind of brings it back classically, sort of, I mean, brings it back to 0 and 1 is measurement. So when we end up measuring the qubit, we finally end up with either a 0 or 1. And yeah, and that is governed by the probability amplitudes, and it's all probabilistic. It depends on the coefficients of 0 and 1. And yeah, that's how qubits work. That's the complete summary of how a qubit works. So it's a tad bit more complicated than a classical bit, just a tad, but like it's cool, and yeah, we'll get into some stuff. We can play around with it later. And some examples of real world qubits. So anything when we deal with anything that's really like tiny and governed by quantum mechanics principles, it's really tough to actually. There's a lot of technicalities and physics behind developing qubits. They're really hard to build. You know, we're dealing with quantum mechanical stuff. You know, it's tiny stuff. But in the essence of it all is just that we like. So I don't know if the 11th graders would know this, but the 12th grade people and other people, uh, something that's quantum mechanical that we can kind of play with is energy levels. And if you guys remember, in different atoms, they have different energy levels. And when we apply EM radiation, we can control sort of uh, the energy levels of the atom and stuff like that. So that's basically what's being exploited when we develop qubits. Either we make artificial atoms, like not like some like Tony Stark stuff, but like using some electrical circuits, we kind of create some mimic an atom which has two energy levels, or we use an ion, which ion is just something that has charge, and we can. Why we use ions is because we can trap the ion, and then we can because electrostatics, we just put it in some place where there's like opposite charge and stuff like that, and it'll just stay there, and we'll just so in both the cases, artificial atoms or trapped ions, we kind of confine the atom or artificial atom, and we just apply our own radiation on it to uh, you know uh, play with the energy levels. Specifically, we'll have two distinct energy levels that will represent the 0 and 1. And yeah, so, superconducting, oh, sorry, superconducting circuits, um, they're microscopic energy engineered electronic loops on silicon chips, just basically an artificial atom. And so these are timed by microwave pulses, EM radiation again. And this is the most famous one, I'm guessing, superconducting circuits, because it's used by IBM, Google, and uh, Rigetti. And the other one, trapped ions, like I was mentioned, I am pretty the best atom to use, I guess, is the ytterbium. And again, we use some uh, EM radiation. We radiate it on the atom, and uh, we yeah, we can control the energy levels and stuff like that. And again, we get a qubit. And this is used by IonQ and Quantum. So I'll be handing it over to Ranesh now. Let me just see if you guys have any doubts. One second. Isn't your dimensions? Wait one second. All right. Uh, wait. Where does it start? All right. Grade 11. Oh, you want me to? Okay, I'll represent tensor product. I'll do that. And okay, wait, never mind. I think it's clear. Okay. Uh, yeah. Okay, I don't think we have to get too into tensor products, but I think Rajiv kind of explained it well. Yeah, we're basically increasing the dimensions of the space and stuff. Sounds really hard, but for now, just think about it as a way to represent two independent qubits. Uh, where there, yeah, so increasing dimensions kinds of represents uh, two independent qubits. I think that should be enough for now. But yeah, it actually is way more interesting than um, yeah, it sounds cooler as well, increasing dimensions. So I think that's it. No other doubts. Yeah, okay, fine. I'll give it to Ranesh now. Okay, yeah, Ranesh. Go for it.
Yeah. Right. I'll just share my screen. Give me a second.
Yep.
Uh, yeah. Can you see my screen?
Yeah, I can see it.
All right. Right. So, hello, I'm Ranesh. Before we start, like, this is just the QR code you have to scan for the G form to fill out your attendance. I'll just wait here for some 30 seconds while you people scan it, and then I'll start with my part of the presentation. All right, I'll go to the beginning. So now Roth has spoken a lot about qubits, and they are extremely important. But the only way we can actually compute in the compute part of quantum computing is when we are using logic gates. The logic gates are there to perform particular operations on a qubit. So I will be speaking about logic gates both in the classical sense as well as in the quantum sense. But before that, I want to just speak about how we can visualize the qubits. So this is done via the block sphere. So as we had discussed, a classical bit can be in one of two states, either 0 or 1, which are just here, the z-axis, 0 and 1. However, a qubit is in the superposition of multiple states. It is not just a single state. Therefore, if we want to represent a single qubit visually, we use this thing known as the Bloch sphere, invented by physicist Felix Bloch. So every point in the Bloch sphere represents an independent, a possible state of a qubit. So we want to know what the z-axis, the x-axis, y-axis all represent. So the z-axis here represents 0 and 1. The y-axis, the x-axis represents what is called the plus state and the minus state. So the plus state is nothing but what is just 0 plus 1, which I'm writing in the bracket notation. I apologize for the handwriting. Divided by root 2. And in the minus state is just where we take the negative of that. Similarly, the y-axis, positive and negative, represent plus I and minus I, which is the same as the plus and minus state, except that there is a I, which is the square root of minus 1, which as a multiplicative factor to your 1. Now, let us see how we are actually going to explain it. So we know that in a normal Cartesian plane, let's just forget about the sphere or anything like that for a second. If we have a plane like this, if we want to represent a single point, we have to use three coordinates, that are the x coordinates, the y coordinates, and the z coordinates to represent a point P. But here, now that our block sphere is a sphere, the x, y, and z coordinates are not independent. They are actually related via the equation of the sphere, which is just x squared plus y square plus z square uh, equal to r square, where r is the radius of the sphere. So now we can see that if we know the x coordinate, the y coordinate, and the radius of the sphere, we already can find out the z coordinate. The z isn't actually independent. So we can say that there are actually only two independent states in the qubit, the x and y coordinates. But this is a rather difficult way of representing it. We prefer a different notation, which is known as spherical coordinates. So let us take this arrow on the block sphere, and let's say its radius is 1. So first we want to find out what the radius actually is. So what the radius represents here is the probability of finding the total probability of finding the qubit in any particular state. So we know that a qubit can be represented as some alpha times 0 plus some beta times 1. Any qubit, regardless of its actual state, regardless of whether it's in a purely classical state or not, can be represented as a combination of alpha and beta. And as Rohit had discussed before, we have alpha square plus beta. Alpha square represents the probability of it going to 0, and beta square represents the probability of the measurement becoming 1 upon performing the measurement. But we know that the probability of finding a qubit has to be equal to 1. It has to be either 0 or it has to be 1. It cannot not be a qubit in any sense of the term, right? So we have this extra equation, alpha. We can easily say that alpha square plus beta square has to be equal to 1 over here. And this is just a basic equation from the laws of probability. And we can finally say that the radius of this arrow on the block sphere, the radius of the block sphere, just represents the probability, the square root of probability to be more precise. So r is equal to square root of alpha square plus beta square. And this is just 1, as we had discussed before, because alpha square plus beta square is 1. So we already know the radius of the sphere. And to simplify our representation further, instead of using the x, y, and z coordinates, where it's difficult to see the fact that they're all related, we prefer using what are known as the spherical coordinates, with the radius, the angle with the z-axis, known as theta. And if we take the projection of this arrow on the xy plane, and it will have an angle of phi with the x-axis. So that's our third coordinate. And since r is equal to 1, we just really need only 2 coordinates to represent this qubit, that is theta and phi. Right? So this is just explaining the same thing. It's the radius of the sphere is always equal to 1. And now what is the point of the block sphere? It enables us to easily visualize the logic gates because of the fact that a logic gate, which is performed on a single qubit, note that the block sphere can only be used for single qubits. It can't be used to represent multiple qubits. It allows us to visualize the logic gates as just a rotation about any of the particular axes that we have, x, y, or z. Right? So now let's speak about logic gates, which is the heart of quantum computing or any form of computing, really. So in a classical computer, what a logic gate does is it takes in a specified number of inputs, can be any number of ones and zeros, depending upon the logic gate. And the inputs have to be binary because of the fact that in a classical computer, there can only exist a 0 state or a 1 state, nothing in between. And it takes these inputs and it gives us a binary output that is 0 or 1. It can't really give you an output of, say, 2, based upon a set of predetermined rules. So the 3 most famous classical logic gates are the NOT gate, the AND gate, and the OR gate. The NOT gate is the simplest of the lot. What it does, it takes in a single input, binary input, let's say 1 or 0, and then just gives the exact opposite. So if it takes in an input of 0, it gives us an output of 1. If it takes in an input of 1, it gives you an output of 0. Then the next two gates are taking two binary inputs. That is, it can take in A and B, where A and B are both can either be 0 or 1. And the AND gate can be understood as something similar to multiplication. It returns an output of 1 only if the two inputs are 1 and 1 respectively. Otherwise, in any other combination, 0 is 0 for A and B, 0 and 1, 1 and 0, it gives us an output of 0. Similarly, the OR gate can be visualized as a kind of addition. So if it only gives you an output of 0 if A and B are 0. Otherwise, it gives us an output of 1. 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 in this case, since it has to be a binary output, not actual arithmetic output, is equal to 1. So similarly, a quantum logic gate exists, and these quantum logic gates are similar insofar as it applies on a specific qubit under a specific set of rules. However, it has to be able to act on any combination of zeros and ones, not just any qubit. And they are visualized as the single qubit gates. Again, there are multiple types of logic gates which can take in both zeros and ones, but I shall only be explaining the single qubit gates in this presentation. They are visualized as rotations about the block state. So the first logic gate is the X gate. We'll ignore the matrix form for now. I shall explain how it comes about. So the X gate can be visualized as a 180-degree rotation about the X-axis. That is, in this block sphere, if you have a qubit, which is represented as psi, the X gate is just a 180-degree rotation about your X-axis. So what it does is that it flips your input. It acts as an analog of the NOT gate. So if it takes an input of 0, it gives us an output of 1. And if it takes in an input of 1, it gives you an output of 0. So, okay, we have got how it works on zeros and ones, but how can it actually work on multiple qubits? So what I'm going to do here is we're going to assume a qubit as alpha times 0, written here, plus beta times 1. Right. And in order to represent the X operation, what we're going to do is that we're going to just write an X over here to represent the fact that there's an X gate which is being used on this particular qubit. We use the fact that as X times X operating on alpha of 0 plus X acting on beta times 1. And finally, we take the alpha and beta out, and then we just apply the X on 0 and the X on 1. And we know what it is going to do based upon our X gate, based upon our truth table. So you get a final output of alpha times 1 plus beta times 0. Okay, but a better question would be to ask why exactly it is linear. Like, is there any particular reason for it? And this is the main reason we actually use the matrix form, because it demonstrates why we are having a linear operation. So what we do is that we consider the qubit 0 as in the matrix form as representing just zeros as a 0 and 1, as a column vector of 0 and 1. And similarly, the qubit 1 is represented by a column matrix with 1 in the first row and 0 in the second row, right? So, and this is how our X gate looks in the matrix form. So we can, now you can just perform the calculations directly. You can substitute 0 as this, you can substitute the 1 as this, and you just perform regular matrix multiplication. And in that case, when you perform it, you get the same output. You'll eventually end up getting alpha times 1, 0 plus beta times 0, 1, which is nothing but the same output that we had received before, alpha times 1 plus beta times 0. This principle of linearity will apply to all our logic gates. So now, similarly, we take the Z gate. The Z gate performs a 180-degree rotation about the Z axis. When it is applied on 0, the qubit remains the same. However, if you apply it on 1, the qubit becomes the negative O1. So what does negative O1 even mean here? It just means that there's a phase factor which is being applied that changes the uh, how the qubit is evaluated, the phase of the qubit, and therefore, if you want to apply the Z gate on again any random qubit, alpha times 0 plus beta times 1, we again use our principle of linearity, and we get our final output as being nothing but alpha times 0 plus, it's my apologies, alpha times 0 plus beta plus beta times minus 1. I just 1 second. Alpha times 0 plus beta times minus 1 based upon our truth table. And we use the same logic with the matrix multiplication. This is our Z gates matrix form. 0 remains the same thing that we had represented before, that is 0 and 1 is 1 and 0 in the matrix form. And we can perform the same calculations and find the same answer. And finally, we have the Hadamard gate. The Hadamard gate is rather important because it's used to create a superposition. So what it does is it takes in a classical input. Let's say it takes in an input of 0, and it converts it into a superposition. It makes it a combination of zeros and ones as follows. If we take an input of 0, it gives us 0 plus 1 by root 2. If you take an input of 1, it gives you 0 minus 1 by root 2. And the matrix form is again represented here, and you can actually see how the matrix multiplication is taking place. This is just our qubit of 1. And when you apply it, you get your required answer. So now we'll go to Bell's experiment. Now, but so far when we speak about the quantum world, we are saying that measuring something actually just changes. Measuring something is extremely important. We don't know the state before. And when we measure it, we get an output that is extremely random, that is probabilistic. Now, this makes no sense, especially from our classical intuition of the world. And many scientists agreed that it made no sense, most famously Albert Einstein, who was also responsible for the special theory of relativity and the general theory of relativity, and one of the most distinguished scientists of the 20th century. He believed that there were hidden variables in a quantum theory that we really did not know about right now. And these hidden variables, if you were to find them, would enable perfect predictions. So he wrote a paper known as the EPR paper, named after the scientists Einstein, Podolsky, and Rosen, which served as a thought experiment showing that quantum mechanics was missing an essential component, which would allow us to make perfect predictions. Later, a scientist, John Bell, realized that it was possible to differentiate between a probabilistic world and a world which had hidden variables via an experiment. But before we do so, I'm just going to speak a little bit about entanglement, so that there's some physical understanding of what is going on. So what entanglement means is that if you have two qubits or two quantum states, and you measure one of the quantum states, the other quantum state the other qubit is at, let's assume, an infinitely far distance. You have Q1 and you have Q2, which are separate, which let's just say are the opposite ends of the universe. Right now, you know nothing about Q1 and you know nothing about Q2. We just know that there's a probability of getting a particular output. If you measure Q1, and we get an output, let's just call it O, for example, Q2 also immediately loses its quantum state, and it collapses to an output which is determined via the how the entanglement actually worked, which we'll represent as O prime. So if you want a classical version of it, you can just assume that there are two balls which are attached by a rod. If you rotate one of the balls, the other one also rotates. That's a similar example. But in this case, it's even more spooky, as Einstein had described it, a spooky action at a distance, because they're quantum, you have no idea what their states actually are. But the moment Q1 is measured, the entanglement collapses instantly. The information travels from Q1 to Q2 instantly. And this is not supposed to happen, according to Einstein's special theory of relativity, that it says that information can only travel at the speed of light. This was one of Einstein's other objections to the quantum mechanical world. So let's start with Bell's thought experiments. Right. So we say that there are two people. There are Alice and Bob. Alice has a particle. Let's say the particle is one. Bob has a particle two, and we are assuming the world is classical, which means that it actually has a property. We do not know what it has an intrinsic property. It doesn't depend upon us measuring it. There's no probability involved whatsoever. And let us just assume that the properties are Q and R for Alice's particle, and Bob's particle has S and T. Q can be either +1 or -1. We don't know until we measure it, but it has an intrinsic value. Similarly, our S and T can be +or -1, which is intrinsic and or objective, and we just don't know what the thing is. That's the aim. We're going to perform a measurement, and we're going to find out. So what we first do is that we take Alice and Bob to separate ends of the universe, or you take them apart to such a far distance that information cannot travel from Alice to Bob at all. So that is preserving Einstein's special theory of relativity. And to prevent any measurement bias from accumulating beforehand, such as they are choosing which properties to measure, and therefore we are getting a particular output, Alice and Bob are randomly going to decide which property to measure by flipping a coin. Let's say this is a random example. Now we're going to take this very particular expression, Qs plus Rs plus Rt minus Qt. You can just factor it pretty easily by using the laws of algebra as Q plus R times S plus T times R minus Q. And we know that both R and Q have to be +or-1. And therefore, there are two cases. Either Q plus R is equal to 0 or Q minus R is equal to 0. And similarly, since either of these have to be equal to 0, let's just assume Q plus R is equal to 0 for the time being. If you perform the calculations, you'll be able to see that Q minus R will either be +or -2 because of the fact that they are either +or-1. And similarly, if Q minus R is equal to 0, then your Q plus R is going to be +or-2. There are like no other possibilities that are involved. Similarly, we know S and T are +or-1, and therefore this entire expression, Qs plus Rs plus Rt minus Qt, has to be either equal to 2 or -2. So so far so good. We've got our expression, and this is either equal to plus or -2, right? And now we are going to try and find the expected value. So why the expected value? We are choosing the properties randomly. We are choosing whether to measure P or Q or R. Sorry, we are choosing whether to measure Q or R or S or T by flipping a coin. And therefore, the value will change based upon our measurements. And therefore, we're going to try to find the bound, like what the expected value is lesser than, or is always going to be lesser than equal to some value X, right? So this is just notation. E of Qs plus Rs plus Rt minus Qt represents the expected value. And it is written as the summation of the probability of choosing Q, R, S, or T times the actual value of Qs plus Rs plus Rt minus Qt. And since we know that this is either 2 or -2, you'll get this expression and we choose 2 here because 2 represents the upper bound. And again, similarly to what we did before in the Bloch sphere to find out the radius, we know that there has to be some choice of the properties that we are measuring. This entire summation of probability has to be equal to 1. Something has to happen. There is no possibility of nothing happening. So we get so its summation has to be equal to 1, and you get this final expression. The expected value is of Qs plus Rs plus Rt minus Qt is lesser than equal to 2. So this is our classical mechanical version, and this is known as the CH-SH inequality, which is named after the initials of its discoverers, CH, S, and H. But now, so far so good. We found out what the classical world is. But what does a quantum mechanical world predict? What does the theory of, it is mostly probabilistic actually say? So we prepare 2 particles with a wave function like this. But what does it mean? So far, you have only seen qubits like this, where it's relatively obvious that 0 is the only possible choice. So we can break it down as follows. Let's just take 0 and 1, 0, 1 ket notation. We say that this 0 belongs to Alice, and this 1 belongs to Bob. And I'm writing Alice and Bob as A and B respectively. So 0 is only affected by the operations, only 0 is affected by any operation that Alice performs, only 1 is affected by any operation that Bob performs. Similarly, we'll take the second part, minus 1, 0. Here, 1 belongs to Alice again. The first qubit belongs to Alice, and the second qubit belongs to Bob. We'll just erase this. Yeah. And the second qubit belongs to Bob. Okay, so far so good. This is our side. And now we have to choose what operations that Alice and Bob are going to use. These operations are similar to just measuring your qubit state. So Alice chooses the following things. These two belong to Alice, Q and R. Here Z1 represents the Z gate, X1 represents the X gate. And Bob chooses these two, S and T, where S is Z minus X divided by root 2, and T is Z minus X divided by root 2. But why these particular choices, right? So let's first check Q and R. So you know that in a Cartesian plane, my apologies, I'll just draw it again. Yeah. In a Cartesian plane, Z and X are orthogonal to each other. That is, you cannot directly express X in terms of Z or Z in terms of X. So they represent the maximum possible angle between two coordinate axes. So similarly, we want the measurements to represent orthogonal properties to each other. And this is why we choose the Z and X gate. The Z gate represents a rotation about the X-axis. Z gate represents a rotation about the Z-axis. The X gate performs a rotation about the X-axis, and it measures the maximum span of properties. Similarly, Bob's two properties, S and T, are perpendicular to each other. So we choose those two. But then there are multiple such combinations. For example, I can take a 30-degree and 60-degree angle here respectively. I can choose, or I can take a 30-degree angle with the X-axis and a 60-degree angle with the Z-axis. So why these two properties in particular? So what this does is when we choose the 45-degree angle, which is what is implied by the root 2, it first says that they're normal to each other. The sum of angles is 90 degrees. And the second is that this is right in the middle of your Z-axis and X-axis, right? It maximizes what is known as the, it maximizes what is known as the correlation between the two measurements. So it has a 50% chance of falling on the X gate. It has a 50% chance of falling of being similar to the Z gate. And similarly for your second set, your T operation. Therefore, we choose these two particular gates to eliminate any possible bias, again, because it has an equal chance of moving to either direction. So now we'll perform Alice's operation. Let's just say Q, because what we want to do is we're going to try and find a similar quantity. We're going to try and find the expectation value of this, which is exactly the same as what we had done in the classical world. So we take Q operator. Again, we only make sure it operates on one qubit, the first qubit, which is Alice's qubit, since Alice and Bob are far enough apart and the qubits don't really affect each other. So you get the following, you get this output. You get the following output here after performing the expectation, after performing the operation. You can see it, 0 remains as 0, 1 changes to -1 and just changes the sign over here. So you've got 0, 1, and 1, 0. Now, similarly, we have to use Bob's S operator because we're trying to find the expectation value of QS. So S operates only on the second half of the qubit, that is the qubits which belong to Bob, which are this and this. And if you find the final expression, it is equal to this value, 0, 1, -1, 0, 0, -1, 0, -1, 1. Now, the expectation value or the average value can be represented as follows. It is the inner product. What that basically means is that you're taking an integral of psi star, where psi star is just the complex conjugate, times the QS operator times your psi, and you're integrating it over all of space. And when you perform this operation, just visualize it as some kind of mathematical thing we are using to find the expectation value. You get the expectation value of QS as 1 divided by root 2. Similarly, RS's expected value, if you do all the calculations, are just 1 by root 2, RT is 1 by root 2, and QT is -1 by root 2. So you get your final equation as this, you get your qs plus rs plus rt minus qt is equal to 2 root 2. But this is the quantum mechanical present expectation. You know that if you remember, when we found the classical thing, the CHSH inequality, it said that the value should be lesser than equal to 2, the classical one. So obviously there's a dissonance between the two, right? There's quantum mechanics predicts it has to be equal to 2 root 2. Classical predicts it has to be equal to 2. So you can perform multiple experiments, which scientists did during the 1980s, and they discovered that the CHSH inequality, the classical inequality, did not hold. That is a hidden variable theory which satisfied Einstein's belief that light information could only travel at the speed of light was not possible. They got the value as 2 root 2, not lesser than equal to 2. Thus, the scientists for performing this experiment won the Nobel Prize. So yeah, that's we have shown that the quantum mechanical interpretation is indeed correct. And now I'll just hand it over to Rohit to continue with the quantum computing part and algorithms part of the presentation.
All right. Yeah. Uh,
Rohit.
wait one second. I think you can hear me. Yeah, 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 I got it, got it. Okay. Yeah, so we ended here. Now I'll be talking about functions in quantum computing and Deutsch's algorithm. And functions in quantum computing, let's start with that. Why I'm going to be talking about that is because representing functions is an essential task in quantum computing, because functions take up a lot of are really important in math when we do math and stuff in any form of computing and computational work. So representing functions when we do quantum computing is going to be really important. And the only reason it's a separate topic right now is because it's not as straightforward as uh, the way we represent functions when we just do basic math. We just we consider a box, and on the right side or on the left side, we'll have an input x, and then on the output, we'll have an f of x. That's basically how we represent a function. Normally, x coming in, box does something, f of x comes out. The reason we can't represent functions like that when we deal with quantum computing is because of a strict condition in quantum computing, which is just that all actions and gates have to be reversible in nature. Another way to say this is they have to be okay, no, actually, no. They just have to be reversible. I think they've written unitary here, and uh, that's an important condition. And if you think about it right now, if you just have a box, and on the left side we have x, and the output we have f of x, that isn't necessarily going to be reversible. I mean, it depends on the function, but it doesn't necessarily have to be reversible. To strictly enforce this reversibility, we have a box with two inputs instead of one, and two outputs. And this is how it's going to look. So this is how we represent a function in quantum computing. Any function we're going to do later on. And uh, yeah, so we have uh, two inputs, two outputs, and when we this seems like way more complicated and unnecessary, but if we just we usually give our inputs as zero. Usually, that's notation. So in this situation, if we just input y to be zero, we end up with x zero. We pass that through UF, we get x and f of x. And this symbol is known as addition mod 2, or basically the exclusive OR gate. So one way to think about this is we have our first qubit x going in stays the same, but when we apply y, when we apply yeah, and the second qubit, there's some y input. The output will be y exclusive OR with f of x, and usually y is inputted as zero, so zero exclusive OR with f of x. Both cases zero with zero, zero with one is just gives f of x. Sorry, so this just ends up being f of x when we input y to be zero and we represent a function. Another thing that we use this representation for is basically if we, instead of inputting y to be 0 conventionally, and we're not trying to just get the function straightforward value, we're going to input this minus state, which, if you remember, is 0 minus 1 by root 2. Yeah. And if we input the minus state with as the second qubit, we kind of what do we say? We experience, or we see that a phase kickback happens, and a phase kickback is just that there is this extra term which is added to the x on the first qubit, which is important to note. Over here, the second qubit had something going on, but when we apply the minus state over here, we end up with a minus 1 to the power f of x term on the first qubit, whereas the second qubit just remains the same. This can be I mean, we can get this pretty easily. We just, instead of assuming y to be 0, if we just apply minus state and we do the exclusive OR with f of x and the minus state, we'll realize that this minus 1 to the power f of x term comes out. And it's actually, the only thing that's notable is that this minus 1 to the power f of x term is attributed to the first qubit, not the second qubit. That's the important thing to note, which is not very intuitive. So yeah, so function represented like this. This is known as a phase oracle. An oracle is just a term we use to call an black box, something we have no idea about inside. And yeah, this is a phase oracle, this is a function, and yeah, that's basically it. So now we know how to represent a function, and we know what more about the phase oracle. So yeah, let's get into it. So now I'll be getting into Deutsch's algorithm, specifically the one qubit case. And sounds uh, why the reason why I've added it to this presentation, or why it's necessary to learn about Deutsch's algorithm, is because it was a really important uh, development in the quantum computing field. Basically, if we've been discussing a lot about the math right now, but I'll just get into what compute quantum computing aims to solve. So quantum computers are not trying to just be the next generation of classical computers. They're not trying to be super fast classical computers trying to exceed supercomputers. No. So the way quantum computers and classical computers uh, compute fundamentally is really different. They have their own fundamentals very different, and because of that, they don't actually try to solve the same problems on most occasions. Like, yeah, we can use this new form of computing to solve our basic addition, multiplication, calculator stuff, but that's not what we're trying to do. We're trying to find out and use this quantum computing to solve problems that usually cannot be solved on a classical computer. Not just speed up the computing power, but there are certain problems which can just easier to solve on quantum computers because of their fundamental difference from classical computers. So a good chance is, when you take a lot of problems, the normal problems, a quantum computer won't be able to solve it faster than a classical computer. And it's also important to note that when we actually try to prepare these qubits and all the machinery around it, it ends up costing a lot of money, and it's really hard. So if we are going to be developing quantum computers, we want to not just do like some kids' homework. We need to like actually get some good use out of it, and solve problems way faster than classical computers. And for that, we have to find good problems to solve. Uh, and there happen to be few problems which quantum computers can solve way faster because of its unique nature. And one of the first problems that could be solved was is what I'm going to be talking about right now. I think it was the first, and it was the algorithm that can solve it is known as Deutsch's algorithm, and it's an important proof of concept. Showing that okay, quantum computers can solve some certain problems faster than a classical computer. So I'll get into it. So the problem statement is there is a function which takes two inputs, 0 and 1, and it has an output for either for both the inputs, 0 and 1, and it either outputs 0 or 1 for again 0 and 1. So that sounds a bit stupid, but like basically for there's a function which takes two inputs 0 and 1, and for f of 0 the values it can take are 0 or 1, and for f of 1 it can take either 0 or 1 again. And this leads to two natures of the functions, is what we call it. So if we say that f of 0 is equal to f of 1, which is equal to either 0 or 1, we're saying like the function is constant, it's either 0 0 for both 0 and 1, or 1 1 for both 0 and 1. uh, the other cases where it's balanced, it's another term. We call the function to be balanced if it gives different outputs for different inputs. Like for 0 1, it gives 0 1 or 1 0. That's the two cases. So classically, if you think about this, to figure out if the function is constant or balanced, you require two queries, or basically you need to know the value of both f of 0 or f of 1 to figure out if the function is constant or balanced. Like for example, if you tell me that f of 0 is 0, I still can't comment on the fact or the nature of the function, because f of 1 its value depends, it influences whether it is going to be constant or balanced. So using a single query, it's not possible to figure out if the function is going to be constant or balanced. But using a certain algorithm in quantum computing, we're able to do that, specifically Deutsch's algorithm. So I'll get into Deutsch's algorithm right now. So on the bottom right here, this is the circuit diagram for Deutsch's algorithm. Uh, yeah, so so let's move along the circuit and let's see. You guys can also, I've attached the truth table for the H gate and the X gate here, and you can try using that and try seeing what happens to each qubit as we move along the circuit. Okay. So the first qubit, before entering the oracle, it undergoes Hadamard. Goes through a Hadamard gate, and that, if you remember, it's written here: the zero through a Hadamard gate produces the plus state, or 0 plus 1 by root 2, and the bottom qubit, it undergoes an X gate, and then it undergoes a H gate. So basically, the X gate prepares it into the 1 state, and then when you pass the 1 state through the H gate, we get the minus state. And if you noticed, this when we have the minus state on the second qubit, we are just essentially talking about the phase oracle scenario. If you remember, in the phase oracle scenario, we had the minus on the second qubit. I'll show that right now. But yeah, so I'll show it actually. So when we have something in the minus state and we take any x, we end up with the first qubit undergoing a phase kickback, and this entire thing is a phase kickback, and this minus stays in the same minus state. Okay, so essentially we have prepared the second qubit such that this thing becomes the phase oracle, and then the H gate is there for the first qubit, that's in the plus state. Okay. um, Now it'll be passed through the function, and once it's passed through the function, let's see what happens. So wait, here is the, we're going to be talking about the first qubit. Okay, usually this is just preparing the second qubit. Qubit's function is just basically to prepare the phase oracle. So the first qubit, H gate function, and now we're going to be talking about this place right here. Okay, just before the H gate, what happens? So let's call this place psi 3, and just before the H gate, we see that psi 3 is going to be in okay, wait, let's just take the general form of psi 3. So if you do this phase kickback thing and you write it down, you'll see that psi 3 will be 1 by root 2 into this entire thing here. Just check if you got that, and if not, just try it, I guess. And if you see, if we now just take the two different cases in this, we take f of 0 is equal to f of 1, and we write it down, we get that psi 3 will be in the plus state if f of 0 is equal to 0 and f of 1 is equal to 0. And psi 3 is equal to 1 by root 2 minus 0 minus 1 if f of 0 is equal to 1 and f of 1 is equal to 1. Now, important thing to note when I talked about phase, clearly over here you can just take the minus sign out over here, and the relationship between 1 and 0 is not altered, it's just still going to be the same, the phase difference, the e to the power I, the phase difference is going to be 0 between them. And so you can take the minus sign, it really doesn't matter. It's not too important. Take it out. So now let's look at the case when f of 0 is not equal to f of 1. In that case, we get psi 3 to be, again using this general formula, we get psi 3 to be equal to 1 by root 2, 0 minus 1, if f of 0 is equal to 1 and f of 1 is equal to 1. And psi 3 is equal to 1 by root 2 minus 0 plus 1 if f of 0 is equal to 1 and f of 1 is equal to 0. Again, this is the minus state and this is the minus of the minus state. We can take the minus out. It's a global phase. It's not important. Doesn't affect our measurements and stuff later on. Okay. So what have we got here? So we get that for this constant case where f of 0 is equal to f of 1, we're getting psi 3 to either be in the plus or minus plus state. Okay. And if f of 0 is not equal to f of 1, we're getting psi 3 to be in the plus or minus minus state. Okay. And now we just apply a hedge gate to this. And if you remember, when we pass 0 through the hedge gate, we get the plus state, and the hedge gate is its own reverse. So when we apply the hedge gate on the plus state, we end up with 0. And if we apply the hedge gate on the minus state, we end up with 1. So once we pass psi 3 and we apply the hedge gate, at psi 4 just before measurement, we're getting psi 4 to be either plus or minus 0. Again, the sign doesn't matter. Basically, psi 4 is either psi 4 is going to be 0 if f of 0 is equal to f of 1, and psi 4 is equal to 1 basically if f of 0 is not equal to f of 1. And so the important thing to note is these zeros and ones are deterministically 0 and 1. They're not probabilistic anymore. The state is in a confirmed 0 or 1. They've moved it somehow through the manipulation of gates. We're getting at psi 4 just before measuring the qubit. If the function is constant, we're getting psi 4 to be 0 with 100% probability. And if f of 0 is not equal to f of 1, we're getting psi 4 to be 1 with 100% probability. So when you measure something and the probability of measuring that is 100%, we're going to measure that. So if we're going to measure psi 4 now, and because so let's look at it from the problems view. Okay, so now we don't know what this function does. I prepare my qubits, pass the gate, pass it through the function, and now I'm measuring 0. That means I can say with 100% assurance that f of 0 is equal to f of 1, because there's no chance of me measuring 0 if f of 0 is not equal to f of 1 or in the balanced state. So just using a single query, just passing my qubits through the function once, I'm able to figure out if the function is constant or balanced just by measuring out just measuring the uh, final qubit one. So that's clearly an improvement from the classical case where you require two queries. And yeah, so this is why it's an important landmark or milestone in terms of quantum computing development. And it shows that, okay, there are certain problems which can be solved faster on a quantum computer. And although this isn't the most practical use of quantum computer, like I don't think too many people care about trying to see if some certain function is constant or balanced. We try to we made one of some of the main goals of people working in this field is to develop certain algorithms which can solve more practical problems and stuff like that. And like I think a good example of one such really practical problem that can be solved with quantum computers and qubits in this form of computing is uh, breaking, breaking RSA encryption or using Shor's algorithm. So, using Shor's algorithm, there is this form of internet encryption which is widely used, which is RSA encryption, and that's the backbone of modern day encryption. And it the entire principle behind its encryption is based upon the fact that classical computers cannot resolve a big number into its primes really fast. Like it's a very hard problem for classical computers to do. But the thing is, there is this quantum computing algorithm which can solve or can factorize these huge numbers into the primes really fast. I mean, not really fast. I mean, like in a time scale that doesn't take forever. Like classically, it's exponential. So if we add another digit, it takes billions of years more. But classic quantum computers can solve it with an actual realistic time scale. And it's not. I don't think it's the most noble use of a quantum algorithm, but essentially this algorithm can break all modern day encryption. And yeah, so that's sorry, it's not uh, a nice thing to do, but you it's a practical thing, something that can be used in our world, and it can break encryption. So similar to that, we're trying to find a lot of practical algorithms which can help us out, probably more helpful than RSA, breaking RSA encryption. But that would be good. And yeah, so that's what we're developing quantum computers for, and algorithms and stuff like that. So Deutsch's algorithm was an example of a very basic uh, speed up of, or proof of concept of quantum computers actually doing something interesting, yeah. So I think that's basically it for this session. With that, the session comes to an end. uh, I think questions and all are welcome right now, so you can go on with the questions and stuff. Think my class will take 2 hours. No, class is done. uh, yeah, I think some of my other club people were helping out with the doubts. But if there's anything, who any questions, feel free to ask. I'll be sitting here for like a few more minutes just to see if anybody has any questions. Is there anybody who's going to join IITM like this year, like 12th to shoot? This is so bad. Wait, just pause this. Thank you, Uru. Thank you, man. Thank you. Uh, Thank you for appreciating our work. For like the 10 people, I hope you guys enjoyed. Read up more about quantum computing if you're interested. And yeah, think you can find me on the group as well, in the summer school group if you are on WhatsApp. So you can contact us and ask some doubts there too after the session if you feel like it. Yeah, no problem, man. Thank you, thank you. So I'll be waiting like another minute. If anybody has any doubts, uh, you can ask. I think after that we'll just end the stream. I think that's it, right? Dude, uh, correct me if I'm wrong. Anybody else from Horizon? I can just end the stream now, right? Oh, wait, I have to show some QR or something. No, I think wait. I think Ganesh done. Okay, okay, bet.
Uh, uh,
Correct me if I'm wrong. Anybody else? Yeah, Ganesh. I think it's not required. Okay, I'll end the stream then. Okay. Bye bye. Thank you.